So now in this video, we're going to build a circuit. We're going to use a PNP bipolar junction transistor 2N3906. And you need enough supply voltage in order to keep it on. So that should be about 5.6 volts because that's the Zener diode we're using, plus about 0.6 volts, the emitter to base drop right there, for a total of somewhere around 6.2 volts. So this isn't a precise on-off or something, but somewhere around 6.2 volts. It's going to quickly turn off as the voltage goes down, and above that it will be on fully. So to begin with, we have the PNP bipolar junction transistor. So this is a TO92 package, and so all kinds of transistors look like this, and so they got different pin layouts and stuff, but generally they can handle the same amount of power. So there you can see 2N3906, good to actually look at the part number. And if it starts with 2N and it's a bipolar junction transistor, pin layout should be emitter, base, collector. So other transistors have other pin layouts. So I want to put the emitter towards the top, you know, to make this wiring more simple. You don't have to right there, but this is the system I generally use, working positive up down to negative, and as much as possible positive from the left to the right. You know, we got some integrated circuits like the 555 timer where they kind of put those backwards for you when it comes to the supply rail. So there we go, we put the positive to the emitter up there, supply rail, once we apply power. So it's not plugged in yet. You should wire this up without power applied. And so we have the transistor. Now we have, let's do the load next. So I'm going to swap the order. We got the LED, the cathode, the band down there is headed towards ground right there, and then the anode up a spot. I'm going to actually put the anode to the collector of the 2N3906 PNP bipolar junction transistor right there. And I'm pretty sure this is the 470 ohm resistor. We also have a 4700 ohm resistor. So we'll just kind of quick look at the color code because it's a simple circuit. So that is not blue, that's violet. I don't know how it's going to look when I process the video. But a yellow, violet, black, 470, and then black for no more zeros. And then you put this brown band to the right, that's tolerance. It can be off about 1% according to the manufacturer right here. And these are cheap resistors, so it may be off a little bit more than that, but it'll be, you know, close enough to 470 ohms of resistance in order to use it in the vast majority of cases. It's not a high precision component, but we don't need high precision components for this particular circuit right there. Close is good enough. There we got yellow, violet, black, and then now you can see we got brown for the multiplier, and of course brown, 1% tolerance. So that means times 10 or one more 0, 4700, 4700. And that's the way I like to think of it. And so I actually filmed this before and miswired things. So I'm filming again, being a little bit more careful that I make the right connections. And now we come to our regulated voltage. So we're going to set basically 5.6 volts as long as we got enough supply voltage to the base right there. That's the main thing. And you know, it's not high precision. It will drift a little bit, but it'll be close. So Zener diode, you use it reverse bias. So cathode goes towards where more is positive, and then anode goes more negative. It's specially made to conduct well reverse bias, the Zener diode. Most diodes are not, but there are some specialty diodes where you can pass current through them, reverse bias. And so 5V6, let's take another close look at that. I know the number is not in a good spot, but yeah, there you can see 6, kinda, V, and then 5. So I don't think that's going to show up great. But I looked at it earlier. So it says 5V6 instead of 5.6 V. They put the V where the decimal point would go, because you probably won't see a decimal point, but you will see the V. Be aware of that. So line lead, the anode needs to go towards where more positive, or the cathode towards more positive. So I'm putting the anode to the negative supply there. Cathode headed more positive, and a 10K resistor. So technically, you may think you can get away without the 10K resistor, but when I used the NPN version, so things were wired opposite, the transistor really would not turn off. I think because we had enough leakage current. So we want the leakage current to go that way. The slight amount of current that it lets flow through instead of flowing in that direction, which will keep the transistor from turning off completely. So now the transistor should turn off completely, whereas it probably will not without this 10K resistor. So that's it. It's a pretty simple circuit. So I did, a relatively slow step-by-step build for those completely new to building circuits for the most part, because that's most of my viewers. So we will attach this. A lot of other people know a lot about electronics, have a lot of experience, but most of my viewers probably haven't even built simple circuits. So there we go. Again, it depends on the supply voltage. Right now the output is off, and just in case I miswired something, short circuit or something, I limited the amount of current that will pass to 20 milliamps of current. The LED is probably the weakest component, easiest to fry, and so as long as you keep it to no more than 20 milliamps of current flowing through it, it'll be just fine. But there we go. So we got about 13 milliamps current. That's because we got enough supply voltage. If I go, I'm not going to jump right to 6.4. I'll work my way down. We are going to have less current because of less supply voltage. Something to be aware. So yeah, there we go. 6.6. I think this is even more quick to turn off than the NPN was. We must have connection problems. There we go. That's what it is. Just connection got loose. So that's the thing with these cheap breadboards and alligator clips clipped to header pins, is they can lose connection. So of course this is not off completely. A little current's gonna trickle through the Zener dial, especially because we're above 5.6 volts right there. But very, very low current. If you got batteries, this is gonna save the battery from over discharging. You don't want to go below 6 volts if you got 2 lithium ion batteries. You want to stop before 3 volts each, or a total of 6. And you just recharge them, no big deal. But you don't want to over discharge them. That's the main thing. And the LED gets dimmer. That's going to save battery life. You can see we only got a couple milliamps or something. But now current's going to go up quick because we got more supply voltage, and at some point the transistor turns on fully. So we could also just use the blue LED. Doesn't matter. It's going to work exactly the same for the most part, but blue LEDs are a lot brighter at low current, as you can see there. And so yeah, we'll lower the voltage. So yeah, it would shut off power for pretty much any load, by the time you get to about 3 volts. So this is probably just a low trickle of current, but again, blue LEDs, you don't really need much for them to get bright. So that's another battery saving tip. I think that's why most devices now, you see blue LEDs, this flashlight. When I turn it on, I think that's why. Looks like the flashlight's probably putting a little bit more current than that LED, but not a ton, and we're close to nothing. So maybe it's 1 or 2 milliamps for each of those LEDs or something. Whereas the red LED, if we were lighting up 4 of them, we'd probably need almost at least 40 milliamps of current to get them, really bright. So that I would just add that extra stuff because pretty simple circuit, and not terribly long video. So I think we will end it there. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out links down below. They all help out a lot. I'll see you in the next video.